It's going to be kind of all the sections there. Probably have a move. One of them is missing.
All right. Happy Tuesday. How's everyone doing? It's lovely outside. I'm happy you're inside with me. We have a big one today. This is the last new theory content we're covering this semester. Everything from here on out is either mini exam 5, which is Thursday, or focused on the final project. So that's where we're turning our attention after we get through today. We have a medium-sized one today, maybe on the bigger side. We're introducing a more systematic test. We've talked about essentially t-tests and how we construct p-values with those t-tests. What we're doing today is constructing a more general test, which allows us to test not just single variables at a time, but it allows us to test models compared to other models. We're going to start by talking about causation. And then we're going to talk about models. So that's where we're going. A couple of housekeeping things. Well, first off, look at the cuteness of this child. This is my dedication to economics, is every morning I leave home and leave her behind. What are you going to do? I guess I could be a stay-at-home dad. That might be nice. No, I love being here. So this is the cuteness I leave behind. A couple of housekeeping things. You know you're going to be sad to not see pictures of Maxine over the summer. You can go back and rewatch the live streams. They are there. Housekeeping, homework 5.3 is due on Sunday. So that's covering control variables. This will feel pretty familiar. I don't expect this to take really that much time, but just keep that on your radar. And then homework 5.4 is sort of the synthesis of what we've done in part 5, and that's also due on Sunday. So just keep those on your radar. Those are not posted on Gradescope yet. That'll be up in the next day or so, but they're posted here. The other thing, mini-exam 5 demo is posted, so you can have access to that. This is the one from, nothing has significantly changed from last semester. This is the one that's been up since December. This would be a good resource for you. This covers, mini-exam 5 covers everything in part 5. Surprise. So take a look at that if you'd like. Question for you. If we were to hold a review session tomorrow night at like 5 p.m., how many of you would be interested in coming to that? Okay. Tomorrow. 5? It would cover basically the same material as in the demo. Okay. So I think we're not going to hold it then. I think there's maybe not quite enough interest. Here's the thing. I'm going to be in my office most of the day tomorrow. So if you want to just stop in and ask questions there, what you would do is work through the demo and then come and talk to me if you have questions about what's in it. Does that sound like a better plan? So I'll be around all day. We'll probably step out for lunch. I think the weather's supposed to be nice, so I'll go for a couple of walks. But other than that, feel free to just drop in whenever my little wheel on my door says, please knock. You can come right in. All right. How are y'all doing? How full is your brain?
Pretty cool.
Pretty full? You ready for summer? We're pretty close. On a scale of 0 to 100, how full is your brain? 1? Like 1 out of 100? Solid. Respect. Mine is not that empty. How many of you are above 50%? What about like 75%? 90? Okay, that's okay. We have a little bit more to do, and then we're basically just synthesizing everything from the semester in our projects. And what we're doing in part 6 is just sort of wrapping up, talking about how we communicate with data, but we're not fundamentally introducing big new ideas. Okay, any other housekeeping things I'm forgetting about? Okay, well, it's nice to see everyone. So we're where we left off last time, we had talked about numerical control variables. So we talked through this Pittsburgh housing price example. So I had a bunch of characteristics of housing of houses in Pittsburgh, with square feet, age of the house, number of bedrooms, which neighborhood the house was in, and a bunch of other factors. And what we were trying to do was establish how valuable an extra square foot was for houses. And so what we did is we tried to build a statistical model to answer this question. What's the value of an additional square foot of living area? And we used 10,000 homes. I got this from Pittsburgh directly. And these were some of the variables. And the question we tried to ask was whether we could separate the effect of like the relationship between the size of a house and its property value from the relationship between the age of a house and its property value. And we know that both of these things are positively related to property values. So if your house is newer, it's more valuable. If it's larger, it's also more valuable. We also knew that newer houses are larger. So the question is whether we can sort of disentangle these things. If a larger house is newer and a newer house is more valuable, then can we measure how the extra value of a house simply due to it being larger and not due to it being newer? And that's what we did. So we introduced this idea of a control variable. I showed you this figure. Some of you liked it, some of you didn't. But essentially, when we introduce more variables, we're estimating no longer linear relationships in 2 dimensions, but these are linear relationships in higher dimensions. So when we estimate a relationship between 3 variables, we think of it as a plane. So that's what this is. Vertical axis is log price. One of the horizontal axes is living area. And you can see, like, this is essentially a line in 2 dimensions. Vertical axis is log price, and horizontal axis is living area. And this is the same regression line we're familiar with in those 2 dimensions. It's just we also now have another dimension. So we could do the same thing. Think of the line in those 2 dimensions. So this is what we're doing with control variables. We're estimating all of these things separately. And our interpretation, once we start doing that, gets a little more challenging, but it doesn't get necessarily more challenging, it just becomes slightly different. With a single variable, we were estimating beta 1 as the relationship between log price and living area. So beta 1 was the increase in the log price when we increased the predictor variable by 1. When we have multiple variables, this changes slightly. Now we're saying beta 1 estimates the increase in log price when we increase living area by 1, controlling for the year built. So we're saying now we're comparing 2 houses built in the same year, but with slightly different sizes. We could do the same thing for year built. So we can say this is the relationship between building 1 year later and price, holding living area constant. So what this is doing is allowing us to compare apples to apples. This should connect back in your mind to the Simpsons paradox, where we, it's like once we compared the survival rate across hospitals for the severity of the disease, then our determination of which hospital had higher survival rate actually switched. We don't see the switching in this case, but we do see changes in the estimate. So including these control variables is a pretty important thing to do, and I would say nearly every well-designed observational study includes a lot of control variables when appropriate. When you're running like controlled studies in a lab, you don't quite need as many control variables because you're doing the control in the design of the study. But if you don't have that control, we usually include more control variables. Okay, so this was the question we tried to answer. This is sort of the difference in the way we interpret the estimates with a control variable and without. These were our 2 estimates, and you can see the estimate here actually rounds to the same number, which tells us something. This doesn't tell us that control variables are not important. It told us that in this case, once we control for the age of the house, at least rounded to this number, there wasn't a meaningful difference. We slightly modified this. Once we looked at estimates with more precision, the estimate did change. But this was the main comparison. These are just some residuals. And then we talked about interpreting logs, which we had talked about a couple of classes ago. But this is, when we're using a log outcome variable, it's important to interpret this correctly. In this case, we interpret a beta as a percentage change. Okay, so we talked about the holding constant intuition, essentially allowing us to compare apples to apples. So we're comparing holding the thing constant that we've included a control variable for. Okay, so that's what we did last time. We ran these models in Python. We're picking up with that example in our exercise for today. But before we get there, how many of you like ice cream? Maybe a better question, anyone not like ice cream? My friends make fun of me for this. I say I cosplay someone who likes eating ice cream. Like sometimes me and my friends will go out for ice cream and like just to get together. And it's a running joke that I actually don't really like ice cream, which is a character flaw of mine. So I'm deeply biased. We're going to talk about causality for a second, relating to ice cream. I'm going to try to prove to you that ice cream is bad, which of course it is. So the first thing we'll talk about is control variables with causation. So we'll think about causality and how to be careful with it. And then we're going to talk about R squared and what we call the F test. How many of you are familiar with R squared? Hands bravely high. Nice. And then what about the F test? How many of you have seen the F test before? All right. So we're gonna talk about how we pick models and essentially perform a hypothesis test, but over multiple predictors. And then we'll talk about model predictions. But just to convince you that ice cream is bad, I have this figure. This is, on the horizontal axis, I have cubic meters of ice cream. So cubic meter is like, just for the units of what we're doing, a meter is like this wide. And so think of a box, like a square box with this side, this long of the sides. So this is, the horizontal axis is cubic meters of ice cream, and the vertical axis is deaths by drowning. And what I've done is just measure both of these things. And what you can see is clearly, and I've estimated this model, what you can see is clearly, as ice cream sales go up, so do drowning deaths. Real data. Yeah.
How do you measure the cubic meters of ice cream?
This is just like using sales, and then it's like you just measure how much ice cream is sold. We can go out and like look at, grocery stores, and like ice cream restaurants and such.
Is there a reason you specifically use cubic meters instead of like volume?
So cubic meters is a measure of volume. So it doesn't really matter what kind of volume we use. We could use gallons, which may be more natural, but if we're in the US. But meters is clearly a better, meters is metric, so we like it better. What do y'all think? Ice cream is bad, right? We should ban ice cream. We should do it for the children. Is this causal?
No.
Have any of you seen this example before? Okay. Does ice cream cause drownings? Well, let's look at a couple of explanations. There's this direct causation. If you eat ice cream, that leads you to go swimming more. And if you swim more, then you drown more. You eat a bunch of sugar, you get hyped, you hop into the pool, and you die. So this is one story. This would be the direct causation story. We could also say reverse causation. So we could say, at my grandmother's funeral, we served ice cream. So this is the reverse causation story. We eat ice cream when we mourn. Or I wake up in the morning, I read the newspaper, I see sad news, and I need to comfort myself. I wouldn't personally do that because I don't like ice cream, but maybe you would. Or it could be something else. Something else could be impacting both ice cream and drownings. All right, it's clearly the first one. Ice cream is clearly causing drownings. What if I showed you this picture? So horizontal axis, I just have time. So this is months through the year. And then the vertical axis is ice cream in cubic meters and deaths by drowning. So these are two series. We talked about twin plots early in this semester. This is just a twin plot. Two different axes, but we're plotting time series on both. What about now? Look, when ice cream consumption goes up, we are also increasing our drownings. So clearly this is causal, right? What's going on? Someone tell me what's going on here, especially if you haven't seen this before. Yeah.
It's people go swimming more in the hot months, and also they eat more ice cream during the hot months.
Yeah. Right. So summer months, I go to the pool. I also actually do eat more ice cream in the forced down. No, I enjoyed it a little bit. I don't go out of the way. Yeah, so summer months we swim more and we eat ice cream more. So these are related, but they're not causally related. What's happening is something else is impacting both of them. You're going to, this is I think, a very clear example of where there's no causal story. Like, it's very challenging to come up with these stories. I racked my brain all weekend for ways to come up with direct. No, I just got it from an article. But when you're writing down your project, you're going to find correlations. You're going to find relationships like this, and you're going to be tempted to write down a causal story. You should not. Nothing you do in this class will allow you to make causal claims. There are ways of making causal claims, but they require something in addition to the statistics that you run. No matter what kind of statistics you run, statistics is not enough to establish causation. We have classes devoted to causality, and you can take them. They're great classes. I think Claire teaches one. So if you're interested in that stuff, there are courses devoted to it, which are supplementary to the tools we have in this class. It's a sort of a parallel set of ideas. Anyway, so this is the, we have a relationship between ice cream and drownings, but it's spurious. It's there is a relationship statistically, but it doesn't tell us anything causal. It just tells us that these things are happening around the same time. Okay, so our simple model would look like this, where we try to predict drownings. And this is where we make the turn towards the kind of statistics we're going to be building in our last content class. So if we're trying to predict drownings, we could just do it with ice cream. This would give us a beta 1 that is significant. This would tell us that the true relationship between ice cream and drownings is meaningful. So there are more drownings when there's more ice cream consumption. And a beta 1 here would tell us something, but it wouldn't tell us a causal story. When we include a control variable, adding the confounding variable with a control, like we talked about last class, this would allow us to compare two different months, both with the same temperatures, and check whether there was a relationship between higher ice cream consumption in 2 months with the same temperature, and whether there was a relationship between ice cream and drownings across months with the same temperature. And in that case, if these were the only variables of importance, if it was truly temperature leading us to eat more ice cream and swim more, we would see beta 1 becoming insignificant and beta 2 becoming significant. Including the confounding variable as a control variable allows us to compare appropriately. And in that case, beta 1 would become insignificant, at least on average. Any questions about this? And the reason this works is because including a control variable allows us to compare, in this case, 2 months with the same temperature. So if temperature is the thing that's impacting both ice cream and drownings, controlling for it will remove the relationship between those two variables. Okay. That's the entire story. I prefer the one we started with, that you should not eat ice cream and do it for the children. This is the kind of thing we've been doing in homework. So in homework 4.1, we looked at this basic relationship between BMI and unemployment using the BRFS. So this is like a surveillance study, not surveillance in like a bad way, but from a public health perspective, measuring sort of public health measures. These being two of them. We weren't controlling for anything in homework 4.1. In 5.1, we introduced a categorical control for gender. And what this did was allow us to have different intercept terms. So this is just our basic intercept control model. In homework 5.2, we introduced different slopes. So this is our interaction term model, where we allow there to be different relationships between unemployment and BMI by gender. And then in homework 5.3, you're going to include more control variables, which is going to allow you to be more specific in your claims. This is something we do pretty frequently in observational data. So we can include essentially multiple controls for many, many factors. Many intercept terms, essentially, for each of these groups. And then in homework 5.4, which I just posted, is you're going to actually compare the estimates across these models. And the way you're going to test which model is most effective is where we're turning next. Any questions here? So one of the things with control variables is once you add control variables, you'll be tempted to make a causal claim. The simple story I told with ice cream and drownings, we could nearly completely control for the confounder using temperature, which would almost entirely remove the relationship between drownings and ice cream. But you're not always going to be able to measure that. There would be a case where we wouldn't be able to see temperature, where we just have the two variables in our data set, and we wouldn't be able to see the confounding variable. A lot of times you won't know what the variable is that would confound your data, and a lot of cases you won't be able to observe it. And in those situations, if you don't see it and you don't know what it is, you're still left with the problem of causality. This is what we call the omitted variable bias. There are things you may not know to measure, and there are things that you don't have measured that you can't control for. And we will never know whether we've controlled for everything that we would need to establish causality. Even if we could, in theory, control for everything, we don't know if we have. And that's the problem of omitted variable bias. So we have to be very humble in the kind of claims we can make with our analysis. The next thing is reverse causality. So maybe poor mental health causes unemployment, and maybe it's not the other way around. So we don't know which direction it goes, and it could go both directions. Unemployment is a very challenging state to be in, and maybe that causes poor mental health. But maybe poor mental health makes it harder to hold a job, and so the direction could go that way. And our analysis will not be able to separate these two directions. It just tells us whether there's a relationship between what we've observed. And then the last thing is, so in this example, BMI and BRFS, these are self-reports. So if there are systematic errors in how people report whatever measure it is, this could very directly bias your results. Measurement error is not a problem, but systematic measurement error that's correlated with the thing you're predicting, that can be a problem. Okay, any questions here? So just because we can control doesn't mean we're capable of establishing causality from our data. And in fact, I would go so far as to say no one in this class, in your final projects, will be able to establish causality. I think in my dissertation I was just barely able to, but it's very challenging to do. Okay, but the short story is controls can help. They can't completely rule everything out. But you can get a lot closer to a clear story with controls. Okay, so what do we need to make full model comparisons? How do we know whether including the controls is the correct thing to do? Well, we need two concepts. One is R squared, and the second is an f-test. So that's what we're devoting. These are the last concepts we're covering in this class from a high level. And then everything else is focused on the final projects. The first one is R squared. So this is just a measure essentially of how much variation does the model explain compared to a intercept-only model. The second is the f-test, which is essentially a test of model comparisons. So it allows us to test whether one model is meaningfully better than another. So that's what we're turning to. Any questions here? Do you like that I'm answering all of my questions? I'm not asking you to discuss any. That was too quick of an answer, Casey. This is the definition for R squared, which is 1 minus the ratio of two things. The top thing is what we call the sum of squared errors for our for the model that we're estimating. So this is like we run a model and we want to test how predictive it is. We're just going to measure the sum of squared errors. So how wrong it is in total. These are just essentially the model and then compared to the data. So you remember those little like green lines we drew? The sum of squared errors is the thing we're minimizing in our regression framework. Sum of squared total is the total variation, which is essentially the sum of squared errors if we only used an intercept. So this is our average only model. And what we're doing with R squared is taking 1 and then subtracting off the ratio of these two measures. So we're saying on top, I have the sum of squared errors. So this is the leftover variation from fitting the model. And then we have the sum of squared total. When the model that we fit explains no additional variation. So if including a bunch of predictor variables doesn't improve the fit of our model, the sum of squared errors will equal the sum of squared total, meaning this ratio will be 1. And what that means is we have 1 minus this ratio 1, meaning that our R squared will be 0. So if our model doesn't do anything better than using the averages, then our R squared will be 0. And then the opposite is true. So we have the sum of squared total on bottom. If this doesn't do much and this does a lot, then this number will be this ratio would be very small, meaning R squared would be close to 1. And in that case, this is sort of the basic interpretation. If R squared is close to 0, our model isn't predicting much better than the mean. And if the R squared is 1, then our model is basically doing perfect prediction. This is a pretty useful model, a pretty useful measure. But there are a lot of, I think I see a lot of people using R squared in ways that it should not be used. R squared is not a measure of how good your model is. And I want to show you kind of why, which will lead us into the F-test. Any questions here? So this is these are 3 different models I've run. I have this first one, which is just the null model. So I'm just using 1 as a predictor variable. And you remember from part 3 that this is just going to estimate the average income. I also have 3 other models. I have, maybe if you're in the back, you might not be able to read this very well. Apologies for who wrote these figures. It's so consistent. If I make that joke, someone laughs. So why would I not make that joke? So I'm trying to predict income using age, well, maybe because I've repeated it so many times. So this is our first model. It's pretty simple, just 1 predictor. The second model is using 2 predictors, so age predicting income and education predicting income. So 2 predictors, and then this third one, I have a 3rd predictor, which is eye color. So we're going to try to include eye color as a predictor for income. And all I'm doing here is running each of the models and then fitting them and plotting their R squared. So on the vertical axis, I have R squared for each of them. And you can see some meaningful things. So R squared in the intercept only model is 0. So the way we define R squared is just using that as the baseline. And then you can see roughly 12% of the extra variation is explained by age, and so on. And the last thing you can see is as we go from the second model to the third model, we're increasing R squared slightly. So my question for you is this a good thing to do? Like, is our last model, is this third model better than the second one? It explains more of the variation. So is it better?
I don't really have an answer, but like, would including something like color as a control, does that affect like how generalizable these findings are as, I don't know, overall? Because that just like reflects, I don't know, if it, like it just seems like something that shouldn't actually affect anything.
Yeah, so Jackson's saying like, why is eye color in there? I don't really understand why we would use eye color as a predictor. And that's sort of a good impulse to have. Like, we want to include variables that we would think would be meaningful. If we just dump everything in there, that is a way we can go. But it changes like some of the internal validity of the model. If you've heard of data mining, this is a very useful thing to do in certain applications. It's like we just want to throw every variable at the problem. And we do that when we're trying to make predictions, when predictions are all we're trying to do. But often we don't want to throw everything at it for sort of interpretability reasons. So yeah, that's a great impulse. Like, why is eye color in there? Is it predictive? Well, we're not quite sure. So maybe I asked you a trick question. Is the third model the best one? Casey's saying no. How do we know? How would we establish that model 3 is not the best? It has the highest R squared, but does that mean it's the best? Well, one thing we could do is check the p-value on the eye color coefficient. So if we're including it as a as a predictor variable, we could just test whether it's different from 0. I've actually tricked you. Eye color, I trick you from time to time. Eye color is actually just a random noise variable. And all I'm doing, I actually don't have an eye color variable. What I did is I ran a random number generator and just got random numbers and used those random numbers, which are unrelated to income. I used those random numbers as a predictor variable to predict income. So notice a couple of things here. Random numbers improve the model fit. So I can make my model fit better by including a new predictor that's simply randomness. So whether you're trying to do predictions or make inference, including random noise is not a good thing to do, even if you're just thinking about how predictive is your model. It improves the model slightly. And our question is, how do we know what's noise and what's not noise? Overfitting is this problem. This is the problem of including noise and not signal in our model. So this is clearly noise. And the reason we know it's noise is because I just literally randomly generated these numbers. And we can add fit to the model. So how do we know? Well, what I did here, you may remember a figure sort of like this. It was like the thumbnail from part 3 and the thumbnail from part 4. I ran 8 different samples. In each one of these, I had the same base data, but in each one of these, I randomly generated a new set of random numbers. So in this first one, what I'm doing is running a restricted model, which is no random noise. And then I'm adding in a new random set of random numbers as a predictor. And I'm measuring the difference between the R squared in these two models. So one without random noise and one with. And I'm measuring the difference. The vertical axis here is just R squared. So this is the first sample. You can see I get a positive difference in the R squared. So R squared went up by a certain amount when I included the random numbers. Then I did the same thing in the second sample. I generated a new set of random numbers, and I used that as a predictor variable. These are different random numbers, so my R squared is different, just sampling variation. And you can see my R squared went up again, this time by a little bit more. And then I did it again, and then I did it 8 times. What do you notice here? Well, when I look at this, I notice a couple of things. First off, every time I include random numbers, it improves my model fit positively. This is a general result. Including control variables will never decrease your model fit. Every time you add a new variable, even if it's random numbers, your model fit will go up. So what that means is every one of these things is positive. The other thing to note is that there's a lot of variability. So the numbers are kind of small, but there's still, there is variability every time we run the sample. So does this remind you of some of those figures we did with random slopes in part 4, and then random intercepts in part 3? Okay, so some conclusions here. Every time we add noise, R squared goes up by a little, even if it is only by a little. So here's I think I'm gonna ask you one question today, besides the exercise, and it's this one. I have a figure that I'm about to show you, dramatic pause, and I'm wondering if you know what it looks like. I think you have enough information to know what this histogram will look like. The horizontal axis, I have the change in R squared by introducing a random number into the model prediction. So what happens when we add noise to our models? Even when the noise isn't meaningful. And then on the vertical axis, I'm just going to have the counts. So it's just going to be a histogram over the change in R squared due to adding noise. So just like the previous slide, but we're doing it 10,000 times and then plotting a histogram. Let's take a minute here. Tell your neighbor you wish you were outside. Complain about why we're inside when it's so nice, and then try to think through what this histogram might look like. Take about a minute. Why are you inside, James? Yeah. Class. Same. What class is making you the most tired? It's hard to do you like it? I teach huge sciences. Yeah, it's fun. Yeah, it's a lot of fun. Yeah. It's like, what if the models were built or not? Like, that's yeah, exactly. No, it's fun. Yeah, it's like sometimes these lower level classes, people take it as a after students are they're all there. It's fun. What's up? You tell me.
It's just like
okay. So normal distribution, we can get negatives. Can we get negatives with this? Okay. So we know it's not going to go below 0. Okay. So it won't be, you're saying it won't be exactly normally distributed, it'll be like all positive, but it'll like sort of have a bell shape.
It's funny, it's really cool.
It's not. Think about like we have random noise, which is moving around our estimate. Like, think about how likely it is for something to be very far from zero. Yeah. So if we add a new variable as predicted, our fit will never go down. What's that? Yes. Yeah, but there's more to it. All right, someone want to tell me some answers? I think that's more than a minute. It's nice you like talking to each other, it seems. I like talking at you. So we have that much in common. Okay, that wasn't a funny joke. Okay, Wyatt.
It would be like a clutch at the start, because all that random numbers are not really moving, and it's slowly moving turn off.
Okay.
I don't know if there'd be any that would do a lot of change.
Okay. Yeah, so lots going on around 0. can we have, and then sort of just by randomness, it would,
Like
we have
there's gotta be
some
some
larger,
values that
yeah,
do something
So
more
some-
than just 0.
some values do something more than 0. So maybe we have a distribution. What about 0? Is it going to be symmetric around 0? Like a normal? A normal distribution centered on 0? I see some people say no. Why not?
I was thinking more exponential.
Okay.
Each increase of noise shows less and less improvement.
Okay. So only on the positive side, and then it sort of tapers off.
Yeah.
Okay. That's nice. Anyone look at my slides to answer this question? Here's my histogram. I ran this 1,000 times, and it looks like this. This is not normal. There's a joke to be had there. Most of the errors, most of the differences, the improvements in adding random noise are going to be pretty close to 0. Some of them will be very large, but they'll be very few. So the small impacts are going to be small, and the large impacts are, the small impacts are going to be frequent, and the large impacts are going to be infrequent. So it would look something like this. So this is 1,000 observations. Most improvements are tiny, large improvements are rare, but we can see them. So if you're thinking about a null distribution of adding a new predictor, this is what it looks like if there is no impact. This is our null hypothesis. Our null distribution, just like we had the sampling distribution when we draw new observations. And this is what allows us to run f-tests on new predictor variables. It allows us to test whether adding a new predictor variable to our model improves its model fit. This is what it looks like if there isn't a model fit. And we can do everything we did before with t-tests, but just using a different distribution. This is what's called the F distribution. This is the F statistic. Secretly, I actually slipped in the F statistic on the horizontal axis here. But this is essentially just related to the model improvement. This is the F statistic. I'll just talk you through a few things. There's not a whole lot of deep insight here. Essentially, this is just measuring how much improvement do we have. So the vertical axis, the numerator is the difference between the restricted model. So this is when we have fewer variables, and then the full model, when we've added the variables that we're interested in testing. So the full model is, in our example, was the one with noise, and then the restricted model is the one without the noise. Then we get the average. So this is just divided by the number of predictors. Then on the bottom, we were normalizing by 1 minus the predictiveness of the full model, and then we divide that by the sample size minus p, which is the number of degrees of freedom. P is the number of predictors, k is the number of added variables, and then p is the number of total predictors. Anyway, so this is some math here, if you've noticed. This is how we construct the f-test. The important thing to remember is that the f statistic under our null hypothesis follows a distribution that looks like this. And this is what we call the f distribution in green. This is equivalent to the normal distribution when we're testing model parameters. But here, what the f distribution allows us to do is test the difference in model fit, which allows us to test for model overfitting. Okay, so we're going to do a couple of things here. But essentially, all of the intuition you have from the t-test, from the distribution under the null hypothesis, will carry over to what we're doing here. It's just the shape is different because we're testing the difference in model improvements. Okay, so we're going to do a couple of tests. We're going to test two things. The first one is just testing eye color and adding it to the model. So I have two models. The first one is income, and we're predicting that with age plus education. The second one is adding eye color. And like we did before, we're just going to check the improvement in model fit. Here, the difference, adding, so this is like another sample. Here, the model fit goes up slightly. We know the null distribution. We know what adding another variable should look like if there is no meaningful improvement in the model fit. And we can test this just using the same kind of ideas we did with the t-distribution. It's just the distribution is different here. We construct our F statistic, which the model software will just give you. And it's very, very close to 0. The p-value of this test is the area under the curve more extreme than our sample statistic. Same idea as the t-test. It's just the distribution is different. So our p-value in this case is the entire area beyond our sample. So sample is our red dashed line. Our p-value is the area under the curve beyond that. So our t-statistic is this thing. Our p-value is very, very large. So we interpret this as the probability of seeing something as extreme as what we do under the null hypothesis of no contribution to the model. And in this case, what we're seeing happens most of the time. Okay, so I think adding noise to the model doesn't improve it. Any questions? So I'm going to claim that this is just overfitting. We can also compare this p-value to the p-value from the model that I just ran. So I tried to predict income using age, education, and noise. And what you'll see is the p-value from the f-test is exactly the same p-value as the p-value on the noise coefficient. These are identical. So what the f-test allows us to do is check the probability of noise contributing to our model, which is the same probability as there being a relationship. So the same p-values. Any questions here? So why are we doing this? What if we want to test adding more than one variable at a time? Which you're going to do in your homework. Homework 5.3 adds more than one variable as a control. Sometimes we want to know not whether one additional variable is meaningful, but whether like groups of additional variables are meaningful, which is what we're about to do. Both the t-test and the f-test tell us the same thing, that the noise parameter, the noise variable, is not meaningful. That's the basic idea with the f-test, with one variable. But sometimes we want to test not whether coefficients added separately matter, but what if two variables are related to each other and we want to add them both? How do we test that? That's the question the f-test allows us to answer. Do age and education together improve the model? Okay, so here's how we're going to do it. I'm going to test the full model, which I'm going to claim does not involve noise. So we're going to toss out noise from here on out. It's very interesting to look at, but also not that interesting. So here's our null model. This is just using using the average to predict the income. So R squared is by definition 0. And then we have our age plus education model. And my question is whether this model is better than the first one. We could look at both coefficients separately, but the more appropriate test is to check whether they're meaningful together. Sometimes one coefficient will not be meaningful on its own, but adding two coefficients together will be meaningful jointly. So this is the better test. So what we're going to do is essentially just run an f-test on this. We're going to check whether adding both models together is meaningful. And the way we do that is we find the f statistic using the R squared of both of these models. We get the f statistic, and then we check it against the null distribution, which is the distribution of random noise. The distribution of the f statistics under random noise. And what you can see here is this is a very extreme value. The probability of seeing this is basically 0. So I would say age and education are good contributions to this model. It's very unlikely that this is due to noise. Okay, any questions here? The reason we do this is because sometimes individual predictors are not meaningful on their own, but are important as groups. And the f-test allows us to do that, where the t-test does not. Okay, this is the end of new stuff. The f-test is the last thing we cover in this class. It's sort of the important idea to sort of close out multiple predictors. What we're going to be working on the rest of the semester really is, in what remains of it, is matching the model to your question. We've built up lots of different specific models, but what I hope to have conveyed over the course of the last 2 months is that the models we can build in this framework are very general and really include all of the kinds of linear models that you can imagine. One of them will be appropriate for your project. These are just some of the examples. So like changing with a single group, differences between groups, relationships between variables, adding control variables, looking at groups as control variables and then group-specific effects. We haven't done a lot with time series, but this is something you can do. Although I strongly discourage it, unless you're deep in your project already. But then, you probably don't see your project on this list. You may see the form of the model on this list, but the next step is to take the tools we have and apply them to your data, which will require some tweaking. This is an incredibly general framework. Most of what we do in science uses this framework, although not all of it. Now's our time to turn our attention to applying it. Any questions here? You all want to do that? So in the last few minutes of class, you're going to present to me, no, just kidding. That's going to happen in the final exam period. There's a couple of practice problems here. If you're interested, you can go through them. But this is just a bit of a summary of what we've done. I have an exercise for today. My question to you is whether you want to do that now, or do you want to do it now, or do you want to go outside? How about this? If you want to go outside, now's your chance to leave. The exercise is posted. I'm going to give you, I think, till the end of the week to do it. If you want to stick around and do it with me for then you don't have to do the work yourself. We'll do that together, or just stick around and we can chat. All right, mini exam on Thursday. I'm going to be in my office all day if you have questions about the mini exam demo. And don't forget about the homework. See you Thursday.
What time do you get into your office?
Get it out of the way.
Okay, because I got work now, that's 12 to 6. But I'll try to, no promises, don't hold it. Also, don't hold it. Alright, got you. I'll see you tomorrow. I might see you tomorrow.
Sounds good.
Same with
All right, if you're still here, I think you're interested in doing the exercise. Is that right?
the exercise.
I think I'm gonna have like an active.
Do the exercise. I'm so proud of you. You remind me of Barack Obama.
Okay, so what we're gonna do, this is always fun, a much smaller group. I can tell you all the better jokes. I can tell you that list is 0, or very small at least. Okay, so we're gonna work through using the F-test for the kinds of models we built last time. So like looking at property values. So I'm going to save a copy in Drive, although I don't, that exercise is mostly for you. So I'm just going to load the file path. This is pointing to the last exercise. And then we're just going to load the data, run this restricted model. So this is, we're predicting log price with finished living area, and then we'll run the full model. So this is finished living area plus year built. So in the terminology of last class, we have model 1 and model 3. So we have 1 control variable and 0 control variables. So finished living area without the control variable tells us the value of an additional so without the control variable, it tells us the value of an additional square foot, just period. And then with the control variable, it tells us the value of an additional square foot comparing 2 houses built in the same year. And with these approximations, like rounding to these numbers, they look the same, although there's actually some meaningful differences without the rounding. Okay, so the first thing we're going to do is just compare the R-squareds. So I have, this is for the tables. If you actually take off tables, you can see the R-squared up here. But usually I just print off the tables, and then we can get the R-squared directly. So this is the R-squared for the restricted model, and then for the full model. So this is including age as a predictor variable, as a control, improves the model by the model fit by almost double. The improvement in the model looks like this, which is pretty substantial, especially relative to just square foot. So the question is whether this improvement is real. I just gave you the code here because I'm feeling generous. Sometimes jokes land better when there's a lot of people, and so it's like a different. They're not even jokes; they're just people laugh at them for some reason. So this is just a way to compare between models. So we're gonna, we have our fit model, which is, the full model, which is the one with the control variable. And then we're going to test it using compare F-test to the restricted model. And what this gives us is the F statistic, the p-value, testing the difference between these models, and then the degrees of freedom. We're not going to use the degrees of freedom. We're just going to run the p-value and the f statistic. So this tells us how far away from 0 are we, and then this tells us the p-value. This is a massive number. We're generally looking for like cutoffs of like 2 and 3 would give us sort of standard significance levels, and this is like 1400. So our p-value is basically near 0. So what does this tell us? This tells us this is we'd say the p-value is the probability of seeing something this extreme if age of the house were random noise. So that's essentially our null hypothesis. So we could say extreme under the null, which our null hypothesis is that the age of the house is random noise. What does this tell us about adding year built to the model? This p-value is very small. So adding age is we say generally an appropriate thing to do. Is appropriate. Okay. Or we could say adding age improves the model. Okay, any questions here? So next thing we'll do is we'll test a noise variable. So I'm just going to run, this is literally how I set up the figures in the slide. I generated a bunch of random data like this. So this is just a normal random variable, which is obviously going to be unrelated to our outcome variable. And what I'm doing here is just adding it to the model. So I have noise as a predictor variable. You can see the p-value is very large, which tells us this is likely due to chance, the coefficient here. So this is our slope coefficient, and it's going to be a normal distribution centered on our null hypothesis, which is 0, and we get a very large p-value. And then what we're going to do next is just plot this full model with the noise, and then we'll measure the improvement. So this was our full model from before. This is our noise model, and then we'll just measure the improvement. Here we see basically 0, so it didn't meaningfully change the improvement. The F statistic is very, very small, so that's very close to 0. And then the p-value is 0.912, which is the same p-value as in the single parameter test. So what does this tell us? So the R squared went up slightly, but nearly imperceptibly. What does the F test say? This tells us, the p-value from the F test tells us that this is likely due to overfitting. So this large p-value from the F test tells us this is likely due to overfitting. This meaning the improvement in the R squared is likely due to overfitting. Okay, and I think that's, is that where the end of what I asked you to do? should we delete that question? You can answer it if you like. I'm just going to delete it. Save changes anyway. All right. Sound good? Isn't it nice that you stayed?
It is nice. Thank you.
All right. I'll see you all on Thursday or tomorrow. Hope you're eating.